So for this week in the Chem 250 lab, we will be doing the Grignard reaction. So it's spelled Grignard, but the actual pronunciation is Grignard because Grignard was a French chemist. And Grignard is a very famous reaction, and in fact he won a Nobel Prize for this. So this is one of the first reactions that was reported where you can make a carbon-carbon bond in a very reliable manner, and it's a very efficient reaction. It is still one of the few reactions that is used very frequently to make a carbon-carbon bond. So Grignard reaction happens when you take an organometallic reagent and react it with an electrophilic co-reactant, right? So what I mean by organometallic is you have an organic molecule, which means it contains a carbon-carbon structure, and one of the carbons is going to have a bond with a metal. So organometallic reagents can react with electrophilic reagents to give you a carbon-carbon bond. So in this specific lab, the reagent will be generated in situ, which means in the reaction medium, and that is done based using this reaction. So you'll be taking phenyl bromide or bromobenzene, whichever way you want to say it, but bromobenzene is more appropriate, and you will be reacting this with magnesium. So magnesium is a metal, as you would know, and magnesium is a group 2 metal, which means it has 2 electrons, and here's an aryl halide. And you treat this with magnesium. What happens is magnesium donates 1 electron to carbon, so that ends up breaking the bond. So carbon and bromine will be taking electrons away from this carbon-bromine single bond. So that means there are 2 electrons and they will take 1 electron each. That will end up giving you a benzene radical and a Br radical, let's say. And if magnesium donates 1 electron to the carbon and donates 1 electron to bromine, you will be getting a carbanion and a bromide. And since magnesium gave 2 electrons away, because that's what it would prefer to do, since it is in a group 2, it is a group 2 metal, right? Magnesium is going to get a 2+ charge. This is what we call the organometallic reagent, because it has the organic part and then it has the metal part in it. And since carbon is a non-metal, magnesium is a metal, you can expect this combination to yield an ionic compound, right? And that's what we are seeing. So you have 2 nucleophiles. So this is a nucleophile and this is also a nucleophile that is generated in this step. And between these 2 nucleophiles, the carbanion is a stronger nucleophile because carbon is a much weaker electronegative element. It's a small atom, therefore it is not going to be really efficient in maintaining that 1 extra electron and this negative charge. Therefore, if we have an electrophile in the medium, the carbanion is a much stronger nucleophile to react with it, and the electrophile is now going to be able to make a bond with this carbon. And in this specific lab, the electrophile that you will be using is going to be your methyl benzoate, is going to be that. And the reason why this is an electrophile is there is a carbon-oxygen double bond here, and carbon again loses electrons to oxygen because oxygen is a more electronegative element. So when this carbanion donates electrons to the carbonyl carbon here, there's a carbon. This carbon already has 8 electrons, so 1, 2, 3, 4, 5, 6, 7, 8, and it cannot accept those electrons until it lets go of the pi bond to the oxygen. And therefore what happens is you now end up making carbon-carbon bond. So and since this oxygen is getting that extra electron that the pi bond has given the oxygen, this oxygen gets a negative charge, and we now have a new phenyl ring that has been able to make a carbon-carbon bond. So that's what you get. And once this forms, we are now looking at the mechanism of how the product forms, right? These electrons now go back in between the 2 atoms again. Now if these electrons are given back to the carbon, this carbon, again being an octet containing carbon, cannot accept these electrons to make a pi bond unless it lets go of another carbon oxygen or a carbon carbon bond. If these electrons are donated back to the benzene ring, they just get a reversible reaction. But if these electrons are donated to the carbon, where this carbon lets the oxygen go, you will be getting the next structure, which is going to be what we call the benzophenone. You get that? And since you broke this carbon-oxygen bond and this oxygen gets both the electrons, the co-species is going to be an O minus. And the Grignard can react one more time with the oxygen carbon bond here, and that's why if you look at the manual, you see there are two Grignards reacting. So these electrons will donate to the carbon here, and these electrons are again taken by the oxygen. So this leads to the next step, which is there was already one phenyl ring here, and then there's a second phenyl ring here, and then you get an oxygen with a negative charge. So now this oxygen is not going to go back and let the phenyl ring leave, because phenyl rings are usually not very good leaving groups, but an oxide is a good leaving group because oxygen is more electronegative. It can maintain that negative charge efficiently. So you get the phenoxide. So the reaction is going to sit there, and when you later on work it up with acid by adding an acid, you'll be getting triphenylphenol. You get that. So this is the product of this reaction. So when you take a Grignard, react that with an electrophile such as the one we have here. So this is a co-reactant. You generate the Grignard to get this structure, right? So when the Grignard reacts with the co-reactant, and when you have two equivalents of this species, you get triphenyl methanol. Methanol is CH3OH. You replace each of the hydrogens with the phenyl, you get triphenyl methanol, and this is the compound we are going to make in the Grignard's lab today. So overall, the Grignard reaction is essentially now that you have seen the mechanism, it is if you take two molecules of bromobenzene and react that with magnesium, you get the Grignard reagent. So two equivalents of the phenyl magnesium bromide. Again, this is same as, right, writing 2 Mg2 plus phenyl minus Br minus. This is the same thing, alright? So you get that, and this is the Grignard reagent. And if you react this with electrophilic species like the one we saw, which is methyl benzoate, you are going to get triphenyl methanol. First you will treat this with the methyl benzoate, then you will treat this with acid and water. That gives you the triphenyl methanol. And this is the final product of this reaction. So that's what you should know in terms of the theory behind this reaction. Now in terms of how this reaction is done, what you're going to do is, I will switch to so you'll be taking a round bottom flask, and you will be adding magnesium metal to that, and you will be adding bromobenzene to that, bromobenzene or phenyl bromide. And then what you're going to do is you're going to put a Claisen adapter, which is going to look like that, right? And here you will be taking a separatory funnel, and you'll have the electrophilic reagent here, which is the methyl benzoate. So phenyl C double bond OOCH3, right? The electrophilic reagent you'll be taking here, and to this side of the adapter you'll be attaching the condenser. So I'm sure you all know what a condenser is. It is the one that is used to cool down vapors when it is generated in a chemical procedure, right? So you'll be attaching a condenser here, and you have magnesium and bromobenzene here, and the solvent that is used to carry out this reaction between these two compounds is going to be ether. So ether is a fairly non-polar, but with some polarity, right? It's a fairly non-polar solvent, and this is a separatory funnel which has a stopper here. You can control the flow of liquid through the separatory funnel by adjusting the knob here. So we'll first let this reaction happen between bromine and between bromobenzene and magnesium, and that will create the Grignard, which is phenyl magnesium bromide. and once you have given it enough time, you will now open this and you will drop the electrophilic reagent, and the electrophilic reagent reacts with your phenyl magnesium bromide, and it is going to now produce the triphenyl methanol. Triphenyl methanol, not a single bond, it's 3 phenols, one with one bond each, right? So you'll get that. And after this reaction is over, you're going to now transfer the contents of the flask into a beaker containing water in it and some ice in it, and then you'll be transferring this into the ice water, and after that you'll be adding a small amount of acid to this to make sure that the reaction is completely neutralized, and then you'll be getting a slurry, and that slurry will now be taken into a separatory funnel, and you will treat that with ether, which is going to be the top layer, and then slurry, and you'll be separating the ether layer, which is the top layer, right, into a beaker where you contain your compound, which is a triphenyl methanol, and you'll be removing the solvent by evaporation. To leave behind the compound that you wanted to synthesize. So when you remove your solvent by evaporation, you'll be left with the compound, which is your triphenyl methanol. So that is the lab you'll be doing, and you should know both the mechanism for the formation of the Grignard reagent and the formation of your final product, right? And also you should know how this procedure is performed. So make sure you read the lab now, which should make more sense, and that should be enough for you to do this lab in a clear, efficient manner.